All right, so we did logistical growth curves. Hopefully from last year, you remember if you're in your AB class, we had derivatives, change in the population of, say, some sort of fruit flies or something, would be something like, it would depend on the number of fruit flies, right? The more fruit flies, the faster, and the more fruit flies you make. So therefore, you'd end up with number of fruit flies times K. And so we recognize that the derivative depends on the number of fruit flies. Now, those of you who don't remember that, you might want to wait until you do the differential equations in Chapter 9 as part of the AB class as a review. Okay, but if you do remember, we're going to roll on forward. We're going to recognize how to separate our variables. We're going to write this as 1 over P dP. We'll put all the P's on one side. We put all the T's on the other side. There are no T's, so I'm going to leave it like this. And then I take the derivative, the integral of both sides. And then I'm going to get something like ln, absolute value of P, equals KT plus the constant. And then, whereas the log of natural base E means that I can put my E to the other side and raise the whole thing to a power. Whoop. Press the button again. All right, that's fixed, hopefully. All right, so I swing my E across, and I get E to the KT plus C, and as we remember, that plus C is E to the C, so I can rewrite this whole thing. I need another letter, so I'm going to go ahead and go with B for reasons that just what's what we do in this particular type of problem. I got rid of the absolute value bars, but B could be positive or negative, and so my population looks like B E to the KT, and my graph ends up looking something like this. Whoop. Where my fruit flies are getting out of control forever. Now, in real life, there's many species, many animals, many things like bacteria, which is my favorite example for this, where they go crazy like this. But the problem is they run into the edge of the petri dish, and so the graph ends up looking more like this thing over here. Okay, whereas going up and going up and going up, and then as it approaches the maximum amount, it approaches the edge of the petri dish, it can't get outside, so therefore it tails off towards a maximum population. The maximum population we're going to ultimately call the carrying capacity. So the question is, how do we model that? Well, we say dp dt is still exponential growth, so it's still got to have a kp to it. Then we're going to tack on something interesting. We're going to say 1 minus, and then we're going to say the population divided by L. Okay, and the reason we're going to do population divided by L is we're going to say that the population at some point is going to, the population becomes equal to L, L being our carrying capacity in this equation right here, then what happens is 1 minus 1 becomes 0. So the derivative, the rate, becomes 0, and so the rate tails off and approaches 0. Does that make sense? Okay, hopefully it does. I'm sorry, I can't talk back to you. Okay, with that in mind, then the question is, okay, so if that's our equation, what's our differential equation? Now the problem is that is an icky one. It is indeed. So I'm going to walk you through how to find it, and then we're going to talk about what you're going to do about this particular bit of fun. Okay, so just a reminder, we're talking about the rate at which something changes, the population changes, is equal to some sort of rate sort of thing times the population, then 1 minus P over L forces when L becomes L over L, 1 minus 1 is 0, so the rate drops to 0, and that means I reached my limit and I can't grow anymore. And so therefore my rate has to approach 0 when I have no growth. Makes perfect sense. Now, I'm going to do the same thing we did before. I got to separate my variables, right? And so as I go to do that, got to control my pen. Hold on. All right, got to control my pen again. So I'm going to separate my variables. So I'm going to go dp over here, and I need my p's over here. So unfortunately, look what happens here. I'm going to take everything over to here. I'm going to leave the k behind just because that's what the worksheet does. Technically, I can leave it over there if I wanted to, but I'm just going to go ahead and move it on over like the worksheet says. And then I'm going to look at it and I'm going to see if I can make myself a common denominator. So I'm going to go ahead and do that. So because we know how to do fractions, we should absolutely do that, because otherwise I'm going to have a real tough time doing this. And so I get P, and then I end up with L minus P over L, right? And then this is our right side stays the same. And I'm going to keep going by flipping and multiplying. End up with this monstrosity, which is L over P, L minus P equals K k dt. Now I want to integrate both sides, and still I got to tell you, this is not going to be easy to integrate. Why? Because I've got something on the bottom I can't isolate, and I can't set a u substitution is going to give me a p in the bottom. So I got a real problem on my hands. But then I recognize, oh, hey, perfect opportunity to do partial fractions. So I'm going to go ahead and say this. So L over P, L minus P equals A over P plus B over L minus P, right? And so then I go L equals A L minus P plus B times P. Then I say if L equals P to cancel this first one, and I would get L equals, this first part becomes 0, and I get plus B times, since P is L, it would be L. So I get 0 plus that, and then obviously this becomes L equals BL, and then the L's cancel out and I get B equals 1. So this up here is 1. And then if I move forward and I go, okay, if P equals 0, to make this one equal to 0, I get L equals A L minus 0 all over, I'm sorry, there's no all over. So this becomes L equals AL, L's cancel out, and get A equals 1 as well. And so I get that this thing here becomes the integral of 1 over P plus 1 over L minus P, and it equals, sorry, dP. And then this becomes over here the integral of k dt. All right, so now I'm ready to integrate the thing. So I'm going to go ahead and go ln of P minus ln of L minus P. Now why did I get a minus sign there? I got a minus sign because when I do the chain, if I set U equal to L minus P, du would equal -1, so I need to make a -1, so I'd throw a -1 out in front. Again, if you don't follow that, do it yourself if you want. A perfectly acceptable way to do this equals KT plus C. Now I can't do it like this, and just to make our life slightly better, what we're going to do is we're going to change around our negatives. We're going to make everything negative as positive and positive as negative. So I'm going to write this as ln of L minus P, absolute value, minus ln of P. And again, all I'm doing is I'm changing the signs. So I multiply everything by -1, which means over here I have to add a negative KT and technically a negative C, but frankly that doesn't matter, so I'm just going to write plus C just to keep consistent with my crazy we don't care. Now using my log rule subtraction outside is division inside, so I'm going to go ln of absolute value L minus P over P, and I'm going to leave that like that, equals negative KT plus C. Again, I'm going to swing my E across, and that's going to give me absolute value of L minus P over P equals E to the negative KT. And again, the same trick, this becomes B out in front. Again, if you're not confused by that, make sure you do differential equations, the simple version first before we get to that point. All right, so this is fun. I got to get rid of this P, so I'm going to move it over to the other side. I get L minus P equals, now again, I can do absolute values, but since there's two absolute values, they end up canceling each other out, so I'm a big waste of time playing with those. So I'm just going to keep going. Negative KT. And you get all the P's on one side, and so I'm going to, what am I going to do? I should probably move. I wonder, I probably shouldn't have done that. I probably should have done this instead. Let me go ahead and do this instead. I probably should have just simply said, if I'm going to get rid of those anyways, I'm going to go L over P equals minus 1 equals this mess. And so then I'm going to go L over P equals BE to the negative KT plus 1. And then I move the P over here. BE to the negative KT plus 1 Oh man, I pressed the button again. Hate that. Okay, so then it's going to be e to the negative kt plus 1 times p, and then I'm going to swing this down below, and ultimately I'm going to get this incredibly odd expression, which is 1 plus be to the negative kt equals p. All right, so this is what we've come this far to get. Why? Because we don't want to do this every time. What we need to know is this. We need to know that this is the derivative when I have logistical growth, where this is my carrying capacity, right? And then if that's the case, then this over here would be my equation for the actual population. Okay, so here's my derivative. Here's what I get when I take the integral. Do not do this every single time. In fact, you're going to memorize from point A to point B with no stops in between. Does that make sense? Okay, so you're going to do A to B, no stops in between, and so you're just going to flat memorize it to do problems. Okay? All right, now some questions come up. What is B? B is the thing that makes the constants work. So they're going to give you how much the initial population is. If you don't have a B, you can't modify it. So that's what that does. And K basically represents your rate. Okay, your rate, how fast things are growing. Does that make sense? So it is basically your original exponential growth rate. Okay, all right, so let's go ahead and start tacking onto a problem right now. So this is what we ended up generating. We ended up with a graph that looks like this, which has two concavities, one concave up, then followed by concave up, exponential growth initially, that tails off as it approaches a carrying capacity. And then we end up, this is the derivative equation, and this is the integral equation, and we're going to remember both of them. It's a differential equation for this derivative. Okay, so then we're going to do example 10. Example 10 says, all right, fine. They give you this one. Now they're either going to give you one or the other, or they're going to ask you dumb questions based on a graph. Okay, so they give you this one, and all they did is they said 1 minus p over 4,000. Okay, so now I know what? If it's kp, 1 minus p over 4,000, I know my carrying capacity is, because that's what L is. Carrying capacity is now 4,000, which means there's a maximum of 4,000 elk in this place. And so it says gate coefficient has 40 elk in there. And what happens when you leave 40 elk inside of a forest and it's reasonably successful? They're going to start growing. They're going to grow until they run out of trees to hide behind, right? And so they're going to grow proportional to how close they are to that carrying capacity. They're going to grow like crazy for a little while, and then they're going to get close to the edge and they're going to stop. Okay, so write a model for the population. Okay, so I write a model for the population. So here's my population model. So I'm going to go P equals L. I now know L is 4,000. They didn't give me any other information, so I'm going to go ahead and leave everything else as variables. Now, they then say, okay, what we need to do now is we need to we know a couple things. We know at time equals 0, we're at 40. So I'm going to put 40 in for the population. And I got 4,000. And then I got 1 plus b e negative k. And then t is equal to 0. So initially I have 0 population. This all becomes 1. And so I end up with 4,000 over 1 plus b. 1b must therefore equal 99. Again, this is what makes my initial conditions work, which is the primary job of b to begin with. Next question is, graph the slope field. You're going to go ahead and do that if you want to later on. It's just going to give you a bunch of slopes going up. The model estimate elk population in 15 years. So I need to know another time. Well, they tell me at time equals 5, I have, how many elk? I have 104. So I'm going to go ahead and say, well, I have 104 equals 4,000. When I have 1 plus, now I know b is 99, I go e is equal to this, so I go e equals negative, I don't know what k is. That's what I'm going to find out now so that I can plug in a later time. Okay, so I'm going to pause this briefly. I'm going to instantaneously do all the math, which you should be able to do on your own, but I'll do it a piece at a time in just a moment. So yeah, let's do this. All right, actually I'll finish this on another video, which is awfully choppy, but we'll just deal with it in another video. Okay, all right, pausing.